Good afternoon, children. So, in previous class, we have seen that general trends and reasons of P block elements, that is group 15 elements. So, now we are going to see that chemical properties of P block elements. So, first one is oxidation state. So, the common oxidation state of these elements is -3, +3, and +5. Yes, so the tendency to exhibit -3 oxidation state decreases down the group. Why it is decreases down the group? Due to increase in their size and the metallic character. So yesterday we have discussed when we move from down the group what happens, isn't it? So when we move down the group, what happens to the metallic character we have seen. So due to that, the tendency to exhibit -3 oxidation state decreases down the group due to increase in size and metallic character. And the stability of +5 oxidation state also decreases down the group. So -3 also decreases down the group, +5 also decreases down the group. Next, the stability of +5 oxidation states decreases and that of +3 oxidation state increases. That means +3 oxidation state increases. Why it is increases? Because due to inert pair effect. Now, what happens to the nitrogen? So, nitrogen can exhibit +1, +2, +4 oxidation states. Also, when reacts with oxygen. So, when it reacts with oxygen, it can exhibit +1, +2, +4 oxidation states. Understand, children? Similarly, in case of phosphorus, if you see, nearly all intermediate oxidation state proportionate into +5 and -3 both in alkali and acidic, acid. So nitrogen is restricted to a maximum covalency of 4 because it will be having outermost electrons. How many electrons will be there, children? What is the electronic configuration of nitrogen? 1s2, 2s2, 2p3. Isn't it? So in s orbital, outermost s orbital, 2 electrons are there. In p orbital, 3 electrons are there. Yes, so its maximum it can show covalency of 4 since only 4 1s and 3p orbitals are available for bonding. That means 1 s orbital and 3 p orbitals are available for bonding. Yes, so that is about oxidation state. Next comes to anomalous properties of nitrogen. If you see nitrogen, nitrogen differs from the rest of all the members of this group due to its small size, high electronegativity, high ionization enthalpy, and no d orbitals. No d orbitals are present. We know 1 s orbital and 3 p orbitals are present, and there is no availability of d orbitals, isn't it? So here it has a unique ability to form multiple bonds with itself. It can form multiple bonds with itself and with other elements. Due to these properties, it has a unique ability to form multiple bonds with itself and with the other elements. That means it can form p-pi bonds. Understand, children? As it is not having d orbital, it cannot form d-pi bonds. Why it cannot form d-pi bonds? Because due to the lack of d orbitals. If you see the heavier elements of this group, they do not form p-pi bonds as their atomic orbitals are so large and diffuse that they cannot have an effective overlapping like nitrogen. Understand? So remaining whatever elements are there under the 15th group, they cannot form p-pi bonds when compared to the nitrogen because they are having large size and they cannot show the effective overlapping. Understand, children? Yes. Next, nitrogen can exist as a diatomic molecule with a triple bond. See, look at here. Nitrogen can exist as a diatomic molecule with the presence of triple bond. Here 2 pi bond, 1 sigma bond is present. Understand? So how it can be formed? Because it is having 1 s orbital and 2 p orbitals. Isn't it? With 3 p orbitals. If we see nitrogen single bond, if we see the nitrogen single bond is weaker than that of the PP is weaker than PP single bond because the high interelectronic repulsion of the non-bonding electrons. Understand? So a nitrogen bond is weaker than the phosphorus single bond because why? Because of high interelectronic repulsion. due to high interelectronic repulsion of non-bonding electrons. So whatever non-bonding electrons are there, they are having high repulsion between them. Due to that, nitrogen bonding single bond is weaker than phosphorus single bonding. So here, owing to this small bond length, as a result, catenation tendency is weaker. Catenation tendency is weaker in nitrogen. Understand, children? So if we move to the next properties, see how a reaction with or a reactivity with hydrogen. If you see the reactivity with hydrogen, group 15 elements forms hydrides. Okay, EH3 type hydrides. EH3 type hydrides it forms. So where E is the group 15 elements and H means hydrogen. So if you see the examples like PH3, NH3, ASH3, BiH3, SbH3. Understand what I said? A reaction with hydrogen. So when group 15 elements reacts with hydrogen, they form EH3 type hydrides. Okay, EH3 type hydrides, where E is the group 15 elements. So in the place of E, you can write phosphorus, nitrogen, arsenic, bismuth and antimony. Understand, children? So if we move down the group, what happens? So NH3 is a mild reducing agent. Okay, ammonia is a mild reducing agent. If you see the last one, bismuth, okay, BiH3 is a strong reducing agent. Strong reducing agent. If you move down the group, the stability of hydrides decreases from NH3 to BH3. The stability will be decreased from NH3 to BH3, and also the basicity of hydrides also decreases. The basicity of hydrides also decreases. If we see the order of basicity, see, look at here, NH3 is greater than PH3, is greater than ASH3, is greater than SbH3, is greater than BiH3. So if you move down the group of a 15th group elements, when they react with the hydrogen, it decreases. Basicity of hydrides also decreases down the group. Next, if we see the reactivity towards oxygen. Okay, when this group 15 elements reacts with oxygen, what happens? So it forms two types of oxides, that is E2O3 type and E2O5 type. Okay, E2O3 type, O3 type and E2O5 type. So look at here the examples: P2O3, N2O5, N2O3, P2O5. So if we move down the group, the acidic character of oxides decreases down the group. Understand, children? So the oxide in the higher oxidation state of the element is more acidic than that of the lower oxidation state. Understand, whatever oxides are present at higher oxidation states of the element is more acidic in nature than that of the lower oxidation state elements. So the acidic character of the oxides decreases down the group. So look at here, here nitrogen and phosphorus are purely acidic in nature. Yes, nitrogen and phosphorus are purely acidic in nature, and arsenic and antimony are amphoretic in nature. And next comes to bismuth, they are predominantly basic in nature. And next comes to reactivity towards halogens. So when they react with halogens, so these elements forms two types of halides, that is EX3 type and EX5 type, where X is the halide. Okay, halide groups we know, no? Yes. So here nitrogen does not form pentahalides. Why it cannot form pentahalides? Due to lack of d orbitals. Pentahalides are more covalent than trihalides. Understand, children? Because the elements in higher oxidation state have a more polarizing power. They will be having more polarizing power. And next, if we see that all the trihalides of these elements, so whatever trihalides of this element forms, except those of nitrogen, okay, except nitrogen trihalide, remaining all are stable in nature. So in case of nitrogen, only NF3 is known to be stable, only NF3. Okay, only NF3 is stable in nature. Understand, children? So this is about reactivity towards halogens. And next one is reactivity towards metals. So all these elements reacts with metals to form their binary compounds exhibiting -3 oxidation state, such as like Ca3N2, that is calcium nitride, and Ca3P2, that is calcium phosphide. Not only that, they can also form Na3S2, Zn3Sb2, isn't it? And magnesium 3 Bi2, Mg3, that means magnesium bismuthide. Okay, they can form. So this is some chemical properties. That means when these group elements reacts with the hydrogen, oxygen, and halogens and metals, what happens, what are the products are formed, that we have learned in chemical properties in p block elements. So that is for today's lesson. In the next class we are going to look after how the preparation of dinitrogen will be there. Thank you, children.